In this video, I'm going to be talking about the substitution and elimination reactions, both SN1, SN2, E1, and E2, they're all four, and comparing them and seeing when certain types go and when certain types don't go. So, to start off, we'll compare the SN2 and the E2 reactions. And you remember that they're both similar in that their rate determining step is bimolecular. It involves a substrate coming together with either a nucleophile or a base for the process to happen. So we can just quickly review an SN2 and an E2 process in general terms. Remember, some leaving group, just give it some R groups, and if the nucleophile comes in from the back side, it displaces the leaving group, leading to an inversion of the stereochemistry. Very important. And this kind of a product right here. E2 is similar in that the substrate will react in one step, but instead of reacting with a nucleophile, it reacts with a base. It does this kind of reactivity. And you remember there's this anti-periplanar requirement for the carbon-hydrogen bond and the carbon-leaving group bond. So if those requirements are met, which they are in this case, the base can pull off the hydrogen, simultaneously forming a new bond as the leaving group leaves. You can get a product, an alkene product like this. So you may remember that SN2 reactions occur very slowly with tertiary substrates. So if we have this species, you remember that if a nucleophile wants to attack from the backside, it is going to be very sterically hindered, and this reaction is not going to proceed very quickly at all. However, here's an opportunity to differentiate between the SN2 and the E2 processes. An E2 reaction is actually very competent with tertiary substrates. And that's because instead of going, instead of going into this sterically encumbered area, it is going to a relatively sterically free area and simply removing a proton. So instead of going into this kind of an area, it's more out in the open, and all it has to do is remove a proton to get the reaction to go. So that's one way to differentiate the substitution and elimination reactions, is by having a tertiary substrate if you want the elimination E2, that is, pathway to occur. So let's compare the SN1 and the E1 mechanism now. As you remember, in both cases, the rate determining step is unimolecular. So there's the first step whereby the substrate dissociates with the leaving group. So we can just draw that generically. Just first step dissociation. To form the intermediate carbocation. And then if we're going in an S in one direction, we'll add a nucleophile, and the nucleophile can attack from above or below the carbocation, because both sides are equivalent. We'll get some kind of a product like this. If we're going to attack in an E1 fashion, we're going to add, well, let's just redraw this first of all. So that we have one of our protons accessible. And we can just add our base, which can deprotonate and form the alkene. So comparing the SN1 and the E1 mechanism, you remember that because we're forming this primary carbocation, or not primary, but we're forming this carbocation, that tertiary substrates are always favored because this rate determining step is the initial dissociation. So if we have a more stable carbocation, then the rate determining step is going to be faster. But because we're forming this carbocation in both rate determining steps, there isn't too much of a differentiation in terms of substitution of the substrate. Both cases have quicker rates with tertiary substrates. So the question is, how can we differentiate these further? And the answer is, well, instead of differentiating the substrate, what we can do is we can differentiate the resulting substrate, or not, excuse me, we can differentiate the resulting nucleophile or base that we add. So how can we change something from being a nucleophile to being a base? Well, nucleophilicity refers to the rate of the reaction, so it's completely a kinetic principle. If you want something to be nucleophilic, you want it to have a low activation barrier, and what you can do to make something a better something that's a good nucleophile is going to be charged, it's going to be sterically small, and very important, it's going to be polarizable. If you forget what polarizability is, it's the ability to distort the outer electrons of a substance. So for example, something like iodine, I minus, is very good because it's charged. It's not sterically small, but that's okay because it's very, very, very polarizable. You can imagine that because iodine is so low on the periodic table, it is it's got a lot of electron density, and in its very large outer shells, they're very moldable. You can think of them as kind of a marshmallow shell because you can push those electrons to wherever you want them to be. Other good nucleophiles include thiolates and generically alkoxides. But as you can see, as you'll see in a second, these are also good bases. So basicity is a thermodynamic principle. It just refers to essentially how much does this species want to have a proton on it. A common good base is an alkoxide, and just referring to some numbers in pKa, the typical pKa of a protonated alkoxide is somewhere in the range of 16 to 19. And we can compare that to iodine up here, where the pK of HI is on the order of -9. Some other good bases are sodium hydride. This hydride acts only as a base, never as a nucleophile. So now let's look at some common species which you may run into and decide whether they're nucleophiles or bases. So bromide is a lot like iodide in that it's a charged species, absolutely. It's got a nice big fluffy outer cloud of electrons, so it's definitely polarizable. And the pKa of its conjugate acid, hydrobromic acid, is extremely low. So this is absolutely going to be a nucleophile. Hydrogen sulfide is definitely a charged species, and you should try to remember that sulfur atoms are very polarizable, and the pKa of the conjugate acid is quite low. So once again, this is going to be a nucleophile. Remember I was just talking about sodium hydride, and the hydride is on sodium hydride is always a base. The pKa of the conjugate acid is extremely high. It's always a base. However, I hate to throw some wrenches in here, but you may run into sodium borohydride and lithium aluminum hydride in the future, and these are actually nucleophilic forms of hydride, but for the purpose of SN1 and SN2, E1 and E2, you don't need to worry about these. They'll never play a role. But just remember that there are nucleophilic hydrides out there. Next we get to these alkoxide species, and they are charged, but they're not that small, they're not that polarizable, and in the basic side of things, the pKa of their conjugate acid is relatively high. So they fit the profile for both the nucleophile and the base. And often when you have these species around, there's going to be a competition between both the elimination and the substitution pathways. One of the exceptions to the rule is tert butoxide, and that's because this is quite sterically hindered, which forces this to act more so as a base than as a nucleophile. Remember, nucleophiles want to be sterically small, and this is not sterically small. So whenever you see this tert butoxide, it's probably going to be a base. Finally, we have just simply, in this case, methanol. And this is not charged, it's not sterically small, it's not really polarizable, and it certainly does not want to accept another proton. So this is just a weak nucleophile and a weak base. And if you have this alone in solution, you're probably not going to get too much occurring. So there's a nice table that I've kind of taken from the Klein textbook, which summarizes everything. And really, you want to focus on the left two parts, whereby you're going to have to recognize when you have a nucleophile, and nucleophiles will always undergo substitution reactions. Of course, primary carbons will undergo SN2, tertiary carbons will undergo SN1. And when you have a base, you're going to undergo this elimination type reaction. When you have some kind of a species that's both a strong nucleophile and a strong base, unless it's a tertiary substrate, in which case you're only going to get this elimination pathway, you're going to have some competition between both the elimination and the substitution pathways. So let's go through a few examples, seeing what we can recognize from each example and try to figure out where we're going with each one of these. So I like to start with not the substrate, trying to figure out if what we're reacting with is a nucleophile or a base. And you remember that sulfur anions are very polarizable, so this is probably going to be acting as a nucleophile. And because we have a primary halide, I would say that this is probably going to go through an SN2 pathway. To result in this thioether, like so. Now you remember this sodium hydride, in the next example, always acts as a base. So we know that this has to attack or deprotonate the adjacent hydrogen. But the question is this going to attack in an E1 or an E2 type fashion? Because this is a primary tosyl group. Oh, sorry, for those of you who don't know what a tosyl group is, OTS equals, give us a charge, equals this group right here, and it's just an excellent leaving group. So as I was saying, sodium hydride is going to deprotonate this position, but because we have this primary tosyl group, it's probably going to undergo an E2 mechanism. So let's do that. Let it go. And we're going to get a product like this. In the next example, remember iodine is polarizable, it's charged, the conjugate acid pK is very, very low, so this is our prototypical nucleophile, and we have a secondary tosyl group. So this is, it's going to be a mixture of both SN1 and SN2. Probably the SN2 is going to dominate. And so the important thing to remember for this, because there is stereochemistry, is that in the SN2 pathway, there's this backside attack, which results in the inversion of stereochemistry. So the resulting product is that. In this last example, you see that we have an alkoxide. But it's not just any alkoxide, it's the one I was referring to earlier. It's this tert butoxide, which is a very sterically hindered nucleophile or base. So it's probably, in this case, going to be acting as a base because it's very sterically hindered. So we figured out there that it's going to react in an elimination type fashion. But the question is it going to react with this hydrogen or this hydrogen? What is the regioselectivity of this reaction? And furthermore, if it reacts with this hydrogen, what is the stereoselectivity of the reaction? Is it going to make an E-alkene or a Z-alkene? And if you don't know the answers to these questions, you can go back and watch the elimination videos that have been posted. So if you do remember, what we're going to form in most cases is the more thermodynamically stable alkene in all respects. So that is going to be, in respect with regiochemistry, that's going to be the alkene that is more substituted. So if we remove this proton, we're going to get a monosubstituted alkene. And if we remove this proton, we're going to get a disubstituted alkene. The disubstituted alkene is more stable, so that's the one we're going to attack. Now the next question is stereoselectivity. Are we going to form the E or the Z alkene? Now remember, it's typically the thermodynamically stable one, which is typically the E alkene. So we're going to get this regioselectivity, we're going to get the E stereoselectivity, end up with this product. So a few more reactions. First of all, just stirring this tertiary alkyl halide in methanol. Because it's tertiary, we're probably going to get some sort of a dissociation to start with. And then we have to think about what methanol is going to do. Well, it's, as we were talking about earlier, it's a pretty poor nucleophile and a pretty poor base. So you're probably going to get a bit of both the SN1 product and the E1 product, and it's not really going to go quick, nor is one really going to dominate. In this next example, we have the same tertiary alkyl halide, but we have sodium methoxide, which can be considered both a strong base and a strong nucleophile. But we know that tertiary structures are very, very slow reacting to nucleophiles. You're not going to get an SN2 process with this thing. So what's probably going to happen is you're going to get an E2 reaction occurring. Just drawing this out further. You're going to get the E2 pathway dominating just because the SN2 pathway is not competent at all. So in this next example, we should first take a look at what we're reacting with here. Sodium hydride, which as you will remember is only a base. And we have the secondary alkyl halide. But there's a problem, because to do an elimination reaction, which is what we would have to do since this is only a base, there has to be a proton on a neighboring carbon, and there are none. So this will have no reaction. Finally, we come to this this cyclohexyl derivative, and we are using an ethoxide base / nucleophile, which is both a good base and nucleophile. And because this is a secondary leaving group, we're going to probably expect a mixture of both the SN2 and the E2 product, slightly favoring the E2 perhaps. So let's take a look at both products. Well, the SN2 is pretty straightforward. It's just the same old nucleophilic attack with inversion of stereochemistry. But the E2 product is a little bit more interesting. So if we draw up our substrate,
in the chair conformation, we notice that in its most dominant conformation, where both substituents are in the equatorial position, there are no hydrogens that are in the same plane as the carbon-bromine bond. So, what we have to do put the tert butyl group down, bromine up, and you notice very quickly that this tert butyl group in an axial position is very, very disfavored. So what is actually occurring here is that this species is spending so much time in this conformation simply for energetic reasons that this can't actually undergo an elimination process. So the only product you're going to end up with is the SN2 pathway.